Okay, this is the page 31 video where we're going to introduce the idea of modular exponentiation. So page 31, if you're looking at the readings, so there you go. Modular exponentiation is the problem of computing a to the k in z sub n. So k is some number between 0 and n, and typically a, k, and n are extremely large. So the problem here, the reason we want to do this is in RSA, as we saw in the last video, we have to compute, if we have a message A, we raise it to the magic number E in z sub n and call that number C. So C is sent out into the world, and back at headquarters they compute C to the D in z sub n, and that actually turns out to give A. So this is one of the two core algorithms for the RSA work. So the obvious algorithm is to compute, if you want, say you want 7 to the 128 in z sub 13. So to do that, you could say, well, 7 to the 1 is 7, so 7 squared is 49, which turns out to be 10 in z13, and then we can multiply that to get 7 to the third. We'd multiply 7 squared by 7, which seems like the easiest thing in the world. So 7 times 7 times 10 is 70, which turns out to be 5. And then we'd multiply that by 7 and get 35, which is what? 9, 26. And then we multiply that by 7 to get 63, which is, 11? 52 plus 11, yeah. Then we'd multiply that by 7, and so on. So we'd obviously have to do 128 steps. So I guess I've gone ahead and done the embedded exercise 23, unfortunately. So the answer is to compute a to the k in z sub n takes theta of k steps. That's basically the answer to embedded exercise 23. Sorry, I didn't give you a chance to think about it. It's not a very good embedded exercise. So the more efficient algorithm is going to be, let's switch to a nice clean new page, so we use divide and conquer. And this is just one tiny clever idea. It's not nearly as clever as in Karatsuba and Strassens and other things we've seen, but the idea is if you want to compute a to the 100th, you compute a to the 50th, and then you square it. Because a to the 50th times squared is a to the 50 times a to the 50, which is a to the 100th. So that's cunning. And then you compute, how do you compute a to the 50th? Well, that's a to the 25 squared, and so on. So, of course, it's easier to do it not iteratively. It's the same recursive idea, but instead of thinking recursively, we say to do like 7 to the 128. We would say, well, we could just do 7 to the 1, and then 7 squared is 49. So 7 to the 1, 7 squared, 7 to the 4th, 7 to the 8th, 7 to the 16th, 7 to the 32, 7 to the 64, and 7 to the 128. So we get 49, which is actually, what do we say, 10, and so we square that, we get 100, and that's 9, because 91 is a multiple of 13. Square that, we get 81, which is 3, square that, we get 9, Square that, we get 81. Square that, we get 9. Square that, we get 81. So the answer is 3. But the exciting thing is it only took 1, 2, 3, 4, 5, 6. It only took 7 steps, not 128. So as usual, the divide and conquer has dropped us from theta of k to theta of log base 2 of k. I shouldn't say as usual, it's just the way it often works out if you're cutting your work in half. So that's cool. And I've done, unfortunately, I went ahead and got carried away and did embedded exercise 24 also. So that's embedded exercise 24. This is actually the second time I'm recording this, so I'm being a little sloppy, because the first time all we heard of the sound was static. Okay, so there's one last concept for this little video, is how would you do 7 to the 100? So the answer is you would remember all the powers, 7 to the 1, 7 to the 2, 7 to the 4, 7 to the 8, 7 to the 16, 7 to the 32, and 7 to the 64. All the powers up to the point where you need them. And I've, of course, forgot them, so I don't want to look back, so I'll just quickly do it. So it was 10, 100 was 9, 81, which was 3, and then it settled into this pattern. Okay, so to do this time, I'll let you do embedded exercise 25, which is to finish this work. So I'll pause the video for a second and make sure you understand how you could get 7 to the 100 in z sub 13 if you've got all the powers of 7, 7 raised to the powers of 2. Okay, so I hopefully you did this. So the answer is 7 to the 100 is 7. You just have to figure out what it takes to add up to 100. So 100 turns out to be 4 plus 32 plus 64. So 7 to the 100 is 7 to the 4 times 7 to the 32 times 7 to the 64. And 7 to the 4th is 9. 7 to the 32 is 3. And 7 to 64 is 9, so then we can compute this as 27, which is 1, so the final answer should have just been 9. Okay, so that concludes this video, which is extremely exciting, I'm sure, and next we'll go on to clean up the algorithm a little, and the video that says is named Page 33.